Today we have to discuss an important section in grand canonical ensemble theory, that is density and energy fluctuations. Density and energy fluctuations in grand canonical ensemble energy. Or this question may be also called give correspondence of G.C.E with C.E and M.C.E. Correspondence of grand canonical ensemble with canonical ensemble and micro canonical ensemble theory. What is the reason for considering this topic? Answer is, in grand canonical ensemble theory, the energy E and number of particles are variables. Energy may be any value between 0 and infinity. Number of particles any value between 0 and infinity. So energy and number are variable in G.C.E. But in canonical ensemble, that is C.E., energy variable but number is fixed. But in micro canonical ensemble, that is M.C.E., number is fixed, energy is fixed, or number is constant, energy is constant. So, by definition, all these three ensembles are different. But, however, grand canonical ensemble and micro canonical ensemble and canonical ensemble, they give same thermodynamic results. For example, equation of state by these three ensembles, PV equal to NKT. Why all these three ensembles? Their definition entirely different, but they give same thermodynamic results. What is the reason for this? The reason for the same thermodynamic result can be explained by calculating density fluctuation. Density means number density fluctuation and energy fluctuations in grand canonical ensemble. So, we take this topic as an important topic. First one, density fluctuation calculation. We know in G.C.E, average number of particles in G.C.E is n bar or expectation n equal to summation r comma s nr into probability. Probability e raised to minus alpha nr minus beta s divided by summation r comma s e raised to minus alpha nr minus beta s. Take it as equation number 1. Then differentiate this equation with respect to coefficient of nr, that is alpha. So differentiate n bar with respect to alpha, dou n bar by dou alpha, equal to dou by dou alpha of this right side. But we know differential of u by v is du by v minus u by v square dv. So in like manner, differentiate dou n by dou alpha, then dou n bar by dou alpha equal to du, differential of this numerator. So summation, derivative nr constant, e raised to minus alpha nr minus beta s, derivative of exponential function, same function, into d by d alpha of minus alpha nr minus nr, d by d alpha of minus beta s 0. So du over by v. V means this denominator. Write this denominator at the denominator. So du by v minus u. U means numerator. Write numerator. And then denominator square. V square. Denominator e raised to minus alpha nr beta s whole square into dv. dv means derivative of denominator. So summation r comma s, derivative of exponential function, that function itself. So e raised to minus alpha nr minus beta s into d by d alpha of minus nr, alpha nr, that is minus nr. So dou n bar by dou alpha equal to, take this negative outside, nr into this nr square, into remaining term e raised to minus alpha nr minus beta s by denominator, this value, minus into this last minus, equal to plus. So plus into, this is same function, x into x, so x square. So nr e raised to minus alpha nr minus beta es again nr e raised to minus alpha nr beta es means whole square by denominator square. So we take whole square. In statics, this is written as first term can be symbolically written as minus nr square, so expectation n square, plus second term nr, so n whole square, expectation n whole square. Use the equation number 1. So if you take this expression, the equation number 1 is this expression, it may be written as n by nr then expectation n. So nr square expectation n square, nr expectation n whole square here. In statics we know mean square number delta n square bar, ordinary bracket delta n square bar is called mean square number. Its definition in mathematics is n square minus n expectation n whole square, but our answer is negative of this definition, so we write negative delta n whole square. So negative delta n whole square equal to dou n bar by dou alpha. Okay. Next, our negative delta n bar square equal to dou n bar by dou alpha, but alpha is minus mu by kt. Substitute the alpha at this position, dou alpha, dou minus mu by kt. Take t as constant, then 1 by kt constant. So 1 by kt comes to numerator. Into remaining term dou n bar by dou mu, we take t constant. Then only we can take 1 by kt outside. So 1 by kt into remaining term dou n bar by dou mu at constant temperature, equation 3. Dividing by n bar square on both sides. So divided by n bar square divided by n bar square. We define specific volume of a molecule small v equal to total volume of the molecule by total number of molecules, or capital V by n bar. So from this equation n bar v by small v. Substitute on RHS for n bar. Then left side delta n square by n square. It can be also written as delta small n square by n bar square. Small n means number density. Number by volume. By volume. Then capital N becomes small n. Capital N becomes small n. It is equal to kt by n bar. N bar is v by v. So n bar square v by v all square. So v square by v square. V square divided by v square comes to numerator. Into dou of n bar v by v by dou mu. So kt by v square into small v square into dou by dou mu of v by v. Capital V constant, take it outside here, the v. Then remaining term dou of 1 by small v. Dou of 1 by small v is minus 1 by v square dou v by dou mu t. Okay. Then delta n bar square by n bar square equal to cancelling v square and 1v. So v, capital V and 1v in denominator cancelled, remaining term v in denominator. V divided by v square by v. V square cancelled. Then remaining term v square, this v square cancelled. Remaining term minus kt by v into dou v by dou mu t. Equation number 4. We know there is an expression d mu equal to v dp minus s dt. Learn it by heart. D mu equal to v dp minus s dt. To put second term 0, we take t0, t constant. If t constant, dt 0. So d mu at constant temperature t equal to v dp minus s into dt 0. So dou mu t equal to v dou p. So dou mu is v dou p. Substitute that dou mu at this position of the 4. Dou mu replaced by v dp. Then delta n bar square by n bar square equal to minus kt by v dou v by dou mu. Dou mu is v dp. Then minus kT by V, 1 by V dou V by dou P is called isothermal compressibility K iso. So delta n bar square by n bar square equal to minus kT by V into isothermal compressibility. But by ideal gas equation PV equal to nKT, take n to left side. So PV by n equal to kT. But capital V by n is small v. So P small v equal to kT. So P equal to kT by V. Take dou by dou V of P. But dou P by dou V equal to minus kT into dou by dou V of 1 by V. Dou by dou V of 1 by V negative 1 by V square. So dou P by dou V equal to minus kT by V square. Take reciprocal. Then dou V by dou P equal to reciprocal of this side. V square by minus kT. Substitute this dou V by dou P here. Then delta n bar square by n bar square equal to minus kT by V into 1 by V dou V by dou P. 1 by V into dou V by dou P, V by minus kT. Okay. Minus kT cancelled. V small v, 1 v cancelled. Then we have small v by v. We know small v is v by n bar. So v by v equal to 1 by n bar. So v by v equal to 1 by n bar. So delta n square by n square equal to 1 by n. Take a square root on both sides. For root of delta n square by n square equal to 1 by root of n. This left side term is called root mean square fluctuation in number density. Root mean square fluctuation in number density is 1 by root of n. We know for a statical system n is very large. Then 1 by very large number is very small. So this RMS fluctuation in number density is negligibly small. Means number density in GCE almost constant. Means number of particles almost constant. That is why GCE and CE and MCE give same result. This is the discussion of number density. Okay.